Hello everyone, and welcome to this podcast going over day 9 activities. Since the weather's not cooperating with us this semester, and we don't want to fall too far behind, as I mentioned in the email, I've posted the activities for day 9, and I would like you to go over them yourself, see if you can do them by yourself, and then if you get stumped, or when you're ready to check your answers, then watch the rest of this video. So we had 3 activities for this day. The first activity, so let's just write day 9 here, and activity 1. And in this activity, we're going to talk about a commercially available enzyme called lactate. And we've talked about lactate before when we talked about lactose intolerance. Now what lactate does is it replaces the naturally occurring enzyme called lactase. And what that does is it takes the sugar lactose, which is found in many dairy products, and it converts it to 2 separate monosaccharides, galactose and glucose. So it's this enzyme here. The question this activity asks, would this enzyme work in the metabolism of a different disaccharide called sucrose? And let's remember that this is a disaccharide, lactose is, just as sucrose is. So they're both disaccharides. So the question asks, if you put lactate with sucrose, would that facilitate the breaking down of sucrose into the 2 monomers of glucose and fructose? And as you've been working on this problem on your own, you may have come to this conclusion that this enzyme lactate, I'm going to draw it down here, let's just make up our own active site for it. Let's say it looks like this. And let's say the reason it breaks it down is because lactose comes in here into this active site. Let's say it's kind of wedge shaped, like so. And because it can fit in here specifically, it's allowed to form those weaker non-covalent interactions to allow it to bind tightly into this active site. Once it binds into this active site, it's able to convert it to galactose and glucose. So let's take our enzyme, lactate. We'll draw it the same way with this wedge-shaped active site. And now the question is, does sucrose bind into this active site to create glucose and fructose? And the answer is no. And we'll make sucrose like this, and we'll just make up a shape for it, but let's say it's more of a square shape. It's not able to bind into this active site. As a piece of nomenclature, you should keep in mind of whenever we draw a line with a strike through it like that, that means it's not able to move any further. So this is blocked because every enzyme has a very specific and unique active site that only binds one substrate. That's the key to this question. Enzymes' active sites have the specificity for one substrate. Sucrose won't bind in it. Sucrose, turns out it binds into a different enzyme. And that enzyme would be sucrase. Maybe its active site is more square shaped, so it is able to bind in here. In this way, when people take this lactate for their lactose intolerance, they don't have to worry about this enzyme interfering with other substrates. Okay, that's activity 1. Let's move on to activity 2. Activity 2. Alright, now this activity, we'll talk about a different enzyme, and this enzyme is called amylase. Now this enzyme here, amylase, as you remember, comes from our salivary glands. And we talked about this a couple weeks ago when we talked about how amylase breaks down starches that are found in bread, but it doesn't break down cellulose that's found in celery. But now we want to talk a little bit more about it. So I'm going to draw one of my famous drawings here of a human. Don't be jealous. Alright, now when this human eats carbohydrates, say a piece of bread, so let's just draw it here, bread, they'll eat it in their mouth, and now they're happy of course because they're eating food, and while it's in their mouth, this enzyme amylase will take bread, which has lots of starch in it, and it will convert it to glucose, which then can be used for energy purposes. we know that this occurs because of the enzyme amylase. What we also know is that this enzyme, amylase, is active in the person's mouth. When the person swallows, that bread or any food they have goes to their stomach, but so does all that amylase. So the question might be, is in the stomach, and we'll just make the stomach here, is amylase active in the stomach? And you should know this, right? Because the question tells you that in the stomach it is not active. So let's remove that question mark and just say not active in the stomach. The main difference, as far as the environment's concerned, between the mouth and the stomach is pH. We know that in the stomach, the pH is equal to about 4.0. It's pretty acidic. However, in the mouth, we know that that pH is more neutral, right around 7.0. So part A says, in one or two sentences, using the appropriate vocabulary, explain why the enzyme stops working. So let's draw our amylase enzyme here, and we'll give it an active site that is more square-shaped. And let's label that as the active site. I've noticed, and you probably have noticed too, that my camera keeps sinking, and that's because the tripod that it's on needs to be replaced. So my apologies if that's causing any kind of visual issues for you. I'll try to keep an eye on it. The bread, the starch, after we've chewed it up some in our mouth, can fit right in this active site, right? And after it does that, it converts it to glucose, as we've talked about before. It turns out that this enzyme has an optimal pH of 7.0. So at 7.0, it has the shape it's supposed to have in order to do this activity. Now, when we drop this pH to 4.0, going from the mouth to the stomach, what happens to this enzyme? Well, it turns out what happens to this enzyme is that this lower pH changes the shape of the enzyme. And we'll just draw something like this. There's no longer that exposed active site, so that's gone now. And when starch tries to bind to an active site, it can't find it, and so it's blocked. And so you don't convert any starch into glucose. So this is also blocked. And remember, we call this a conformational change. This can be caused by temperature or pH. There are a few other things that can change it, but you should know these two, temperature and pH. The next question asks us to draw a graph, and it gives us specific instructions. It says along the horizontal axis, make pH. So we can have 1 to say 14. And along the vertical axis, we're going to put enzyme activity, and I'm just going to put ACT, enzyme activity. And what you need to do here is show how the enzyme acts, or its activity, how it changes at these different pHs. So we know that amylase has a peak value of 7. And so we'll put it right here. And we know at a lower pH, and we said around 4, it has no activity. So we could draw it something like this. Now the problem doesn't tell you this, but we also know that at higher pHs it doesn't work. But as far as what the problem tells you, this is really all you could draw, because I didn't give you any data on higher pHs. So if you ended up just drawing this, that would be correct. But just to complete the story for you, at higher pHs, this enzyme also does not work properly, for the same reasons of this conformational change. It requires this optimal pH of 7 in order for it to be active. All right, so the take home from this activity is that at different pHs, enzymes can fold differently. Also at different temperatures, enzymes can fold differently. And when they fold differently, that can change how the active site forms and how accessible it is now to the substrates. This is a really good way to regulate enzyme activity in our body and within individual cells as well. All right, let's move on to the last activity, activity 3. Okay, so let's talk about activity 3 here. And activity 3 resembles more of a type of question you might see on an exam. It's based upon what we learned in activity 2 about how enzymes change shapes when they're exposed to different temperatures or different pHs. So in this question it says, which curves on the graphs may represent the temperature and pH profiles of an enzyme taken from a bacterium that lives in a mildly alkaline or basic hot springs at a temperature of 70 degrees. What this tells us here, the alkaline, it tells us that its activity is going to be the highest at pH is greater than 7. This is mildly alkaline, so it's not going to be like pH 14. It's just going to be a little basic. It also says it lives in a hot spring, so this is not shocking for us to discover that its optimal activity is going to be at 70 degrees Celsius, or at least that's what we would predict since that's the environment it lives in. And in our two graphs here, you can see on the top one, we see temperature, on the bottom one we see pH. And so what we're seeing here are 3 different enzymes. One of the enzymes seems to have an optimal temperature of around 35 degrees, something like that, maybe closer to 37 degrees. The second one has an optimal temperature of around 55 degrees. And then this third one has an optimal temperature of around 75 degrees, somewhere around there. Down here, we see 2 different enzymes. One has an optimal pH of around 4, so more of an acidic pH optimum. And this other enzyme has a pH optimum of 8, right around 8. All right, so the question is, which of these curves represent this bacterial enzyme in question? So let's look at this. Let's first look at temperature. Of these 3 enzymes, this enzyme here, enzyme 3, is optimal at a temperature pretty close to 70 degrees. So of these 3 choices, 3 seems to be our enzyme. Down here, when we take these 2 enzymes and we look at them at different pH optimums, we see that 5 has an optimal pH of around 8. So our enzyme is represented by curves 3 and 5. So of our choices over here, of our answers, the correct answer is going to be E. Okay, that's all I have for these 3 activities. If you have any questions at all, please make sure you let me know. You can send me an email or we can talk in class on Thursday. Presumably we will have class on Thursday, but who knows with this weather. So with that said, have a good day. Stay warm, stay safe out there, and see you Thursday.